So yes, rotating thin disks are scary thing, are very scary in terms of design, in terms of care we need to put into the design of those elements, and also handling those elements. And maybe you don't, let's say that maybe at this point there is nothing that would come to your mind saying, okay, what is John talking about? Rotating thin disks being scary, or a very, say, particular special application. And one of the best ways to demonstrate this is to present a video about an application of where those type of elements are used, and also what are the implications of using them. So, but before jumping into the video, what are thin disks or rotating thin disks? Basically, is a disk. What we call disk is a circular object in cross section, and that is very thin. What we call thin, defined by this letter T. Then you can find in certain literatures that say, well, to be a thin cylinder, then the relation between T and the diameter of the element has to be also kind of between 15 and 20 times or larger than that. Sorry, this is the other way around. Yeah. Oh my goodness, why I'm doing this? T 100. No, it's small. Sorry about that. Just mixed up. There it is. So then we have this relation, and when we say rotating thin disks, it means also that these elements are exposed to an angular velocity. Typically, these elements, these disks, are going to be rotating around one central point that is going to be the center of the intersection of the symmetry axis. And usually you're going to see also that if this is rotating, then you are going to find certain, let's say, well, this is exposed, or there is an angular velocity that is on which this is rotating there. Now, I presented this disk with an internal hole, as you can see in this lateral figure, but rotating disks can be solid completely, meaning that the internal radius defined from this point to this point here is 0, or it can be very small, but in general, I wanted to present this case because it's going to give you the possibilities of taking the results we're going to get here and then apply it to several other cases. So that's on first hand. And also, we're going to see an interesting feature that we could have as a ace to design things that is going to be related on how to have this shape that it's going to guarantee that stresses are going to be evenly distributed across the whole section here, this whole segment here. Perfect. Let's go to the video because it's going to be excellent. And this video is taken from YouTube. This is from actually a Finnish channel. Let me jump here, and I believe you can see it. And the channel is called Beyond the Press. It's called the channel. And they started, I believe, making videos about pressing, using hydraulic presses to destroy things and see what was the react. We could see certain characteristics when they were pressing, for example, glass or paper or rubber. So it was very interesting to see. But in this case, I found it, and they have a very nice shot about what happens when you are handling or working with grinders, most basically. And what is a grinder? And let me find one specific picture of, or elements of, I believe you're going to see it if I create a new tab here directly, and I can show rotating grinder. See, these ones. It's not yeah. For example, this is a grinder. Yeah? So it is a motor, and then there is a disc here, and the disc is used to kind of level surfaces, cut, or remove certain impurities. So you can find maybe certain other examples of a grinder here. Yeah, this one, for example, you can just finish certain surfaces or get them even to do certain other works. But this is a grinder. And this is a very nice application where rotating thin disks comes into play. You can find it also like, rotary, for example, rotary, what is it? So disk. So those are used for wood, for example, or rotating, all these kind of disks here. I believe if you have used certain these Dremel type machines, you can see that they have these small disks that are rotating at very high speeds, and that you use it to cut, to mold, to shape, or any other things. But this type of disks, this is where this topic comes into importance, and we will see why. So let me see here. Go back to the channel, and I'm going to play it, try to describe it. So, well, this was a previous experiment that they did, but this is great. So here they have a rotary disk, and I believe they are exceeding kind of two times the allowed operational rotational speed of this disk. And they're saying, well, what's going to happen? So it's going to do something, it's going to break, it's going to work perfectly. So they started doing it. This is a low speed camera, and then it is rotating until it explodes. And not only that, so these are the fragments of the disk, because actually elements rotating at a high or at a certain angular velocity that is more than they can withstand, so they actually disintegrate, or they actually explode. And let me just run it. And look how this piece of disk just went through the helmet like nothing. And also, if you notice, I'm going to replay it again. The other piece of the disk, just went through this plywood here like it was butter there. So look at that. So it just destroyed everything. So imagine if somebody is operating these elements and the disk is very badly designed, so it could be fatal in this case. It could kill somebody. So designing these elements are, let's say, important, or kind of paying attention extremely to the design of it. Yes. So imagine that if for static elements, we need to be very careful with our design, our safety factors, methods, or failure theories we're using. So when we talk about moving machinery or rotating disks like these ones, so we need to be super careful with the design of these elements. So more consideration has to be given to it. So imagine, let's replay it again. So now I'm going to just try to, well, these are some marks that these previous experiments did on the concrete there. But there it is again. So definitely this is not steel, but what we're going to do here can be related to what's happening here. Actually, one of the exercises that we could do is to determine what is the maximum angular velocity that we should operate certain or apply to certain disk so it doesn't fail because of this. I would say this is impressive. This is scary because it could kill somebody. So a bad design could be fatal. Do you have any questions so far about this? No, okay. So let's come back then to understand the variables involved in the whole design process of this. Well, not design process, because we are not going to design these elements. We are going to answer the questions: what are the stresses that are being formed in the insides of the disks? We are going to relate it to the thickness of the disk. We are going to relate it to the angular velocity of the disks. So we're going to see that all of that is going to modify, or is going to have an influence on the stresses created on the disk. So to that end, what I have here is a circular disk, and I'm going to extract a small portion of the disk, kind of this kind of wedge here, or circular wedge here, that is limited by the points A, B, C, and D, and that there is, well, no, this has some certain thickness of delta R, dr, and there is kind of a small radius of this wedge, or this strap of the circular segment, that is d theta. And then we're going to also mention that, we have an internal radius R1 and an external radius R2. This is rotated at an angular velocity W, and then we have a thickness T. And when I extract this element from here, from this edge here, to this magnifying glass, if I want to call it, so I have still the same elements, so A, B, C, D, so that's the section. But of course, this is in 3D because this has certain, let's say, depth here, something like this. So basically something, so this is not just a plain figure. This is very bad. But this has certain thickness that we need to take into consideration for our representations there. There you go. Now, when we start understanding, okay, but as we have always done, we either start by analyzing how things deform, or we start from the equilibrium of things to try to determine a relation between forces and deformation, or in the most critical case, as we have done it before, what are the relations between stresses and strains by considering the material we're working with. And in this case, we are always going to be talking about steel. That grinder disc you saw in the video is not made out of steel completely. It's made out of composite that has certain solids there, like some carbon silice, I don't know, whatever, just silly. What would be the nice pronunciation for that word? That element would be silica, I believe is the word. Some silica dust or something like that. So it's kind of a mineral oxide of silicon that is very abrasive, and what it does, it just, it can be used as a file or as something to remove material from any steel or anything else. So it's a composite of several things there, and it's not made out of it's not made out of steel completely. The central part, the hub that it attaches to the grinding machine, might be out of steel, but then there is some bonding, some material glued on top of that steel part. But this is made out of steel. And then let's see what happens with what are the forces applied to that segment when I just focus on that segment. And then I just wrote them down here for you. I said, well, the first force that we need to imagine is, well, the force that is happening, well, in the phase AB, well, in this area here, but not as phase AB, but in this region here. So we know that there is a radial stress to begin with. So similar to thick shells, these are round objects, and then we're going to have primarily two types of stresses. We're going to have radial stresses, and we're going to have circumferential stresses, denoted by sigma r and sigma theta here. But then, when we talk about, okay, what are the forces that are being developed by this stress, or vice versa, because it may be the force that is developing the stress. So we have AB in this area here that is going to create a certain surface. If I try to draw it something like this. Okay, so what is the force that is going to be kind of present in this area? Because we have a stress here, sigma r. Well, we know that it's going to be the force is going to be sigma times the area, and the area of this small segment at the bottom of this differential element is going to be what? Well, the area is going to be this circular segment here that is going to be defined by r times delta theta, r going from the origin of the system to the beginning of the differential element, and times this angle, as I mentioned, and then times t, that's going to give me the area, and when I multiply that times the stress there, it's going to give me the force applied here. Now, on the top part also, we're going to have another force, and here we're going to have that not only the stress sigma r is appearing, but something else is appearing, because remember that when we were dealing with differential elements instead of stress, and we took that infinitesimal cube, we said, well, at one point we have one stress, but at the other point we have a stress plus something, which inserts the variation of stresses, positive or negative, from one point to another. So because here what we're saying is that the stress in this area is different from the stress at this area. So if I wanted just to put this a little bit better, I would put something like this. Or I would try to actually remove it a little bit to say that this starts from this place here, and this starts from this point here. So it makes better the representation. There it is. Perfect. But then similarly, what's going to be the area where this stress is going to be applied? Well, it's going to be this circular segment times the thickness, and the circular segment is going to be, well, how much is this angle here? Well, that angle is going to be the same delta theta, the theta. But then the radius is going to be what? Well, the radius is going to be r plus the whole, let's say, height, let's call it, of this segment, which is going to be the r, and then that's why we have the stress times the radius times the angle times the thickness of the surface. So that's going to give us the force in this surface here. Then we have also a circumferential stress, but that circumferential stress is not aligned with the Cartesian coordinate system that I'm using, which is something like this here. So we have these 90 degrees here. So they are following the circumference, but they're not following our Cartesian coordinate system. But when I use the angle, that is the orientation angle from that circumferential direction to my Cartesian coordinate axis, then I can say that, well, you know what, the angles here, or the circumferential stress, this one here is basically this stress times the area presented here, but this area here is the r times t. So that's why it is appearing in this way. And it is similar in both sides, meaning that circumferentially, those two stresses cancel out. But also, as this is rotating, then the mass of the disk needs to be taken into consideration, because the mass times the angular velocity is going to create a centrifugal force. And that centrifugal force is related to, for example, if I consider that the mass is certain density of a material times certain volume, then I could determine how much is the angular velocity by taking into account this, where is it? that here is that basically this is the mass times the angular acceleration, or one of the components of the angular acceleration, which is the radial part, let's call it r, and that's going to give me the centrifugal force. And then this brings me to the fact that this can be rotating at a constant speed, constant angular speed, but still is going to have an angular acceleration directed in the radial, let's say, orientation. So let's remember that when we're dealing, you saw it in the past in the previous courses, that when we are working with an angular movement, the acceleration has two components, to have the tangential component and the radial component. And the tangential component might be zero because the angular acceleration is constant, but we're going to have an angular acceleration in the radial direction. So that's why this appears, even though omega can be constant in this case. Perfect. Any questions so far? So then for us, it's pretty interesting to understand the equilibrium in the radial direction, because the equilibrium in the circumferential direction, it's kind of canceling out each other. So let's start by working with that equilibrium. Let me write it down, maybe here. I will move this one and put it here. It's made out of steel, and then equilibrium in the radial direction. Perfect. So let's try then writing down. And what we're going to do is pretty simple. We're going to say that the inward forces are equal to the outward forces. And that's it. Then what is that? Well, the inward forces are these ones. So we have first the force caused by this radial stress in this surface here, AB, or kind of limited by this AB segment, plus these two components of the circumferential stress pointing down. So let's write those down. So we have the first one is this one, here, times R times T times this one, which is this one here, plus we have 2 times this one here. So, but to convert it into, or to transform it into, from the circumferential direction to my Cartesian coordinate axis, I need to use this angle that is presented here. And that's going to say, well, this is going to be the sine of this vector here. So then it's going to be 2 times this thing here times the sine of the angle. So it's going to be 2 times this element here. So 2 times T sigma R. I'm going to try to write things. No, sorry about that. T dr sigma theta times the sine of that angle there. And that's going to be equal to what? Well, it's going to be equal to what is left here, which are basically 2 forces. One due to one is the centrifugal force, and the second one is related to the radial stress plus the increment or variation of that radial stress on that surface. And that's going to be, so we have tackled this one already. So this one already. So we're missing this one, and let's write it down. So it's going to be sigma R plus this one here times R plus the R, then the theta T plus centrifugal force. And we already have the centrifugal force already summed up here. So it's going to be this density rho square T dr d theta and the angular velocity. Awesome. Any questions so far? Let's continue. So the first change we're going to do is we're going to say, well, let's take a look at this sine of this differential angle divided by 2. So the first thing we can say here is that sine of the angle theta divided by 2, I could consider it to be just because as that differential angle is very small, so I could say, well, you know what, I could get rid of the trigonometric function and say that the sine of this angle divided by 2 is equal to the angle, because that angle is pretty small. So I can say that. So if I do that, and then I introduce back into this equation that we could give them names, maybe equation 1, let's call it like that. Then substituting in equation 1, so we can say, perfect, let's do it. So again, let's write again everything back. RT d theta plus 2. By the way, already, if I'm substituting the sign of the differential of the angle divided by 2 by the differential of the angle divided by 2, then I can right away say, well, no, I can just get rid of these 2 and then say, well, this is equal to this. Then theta and then the theta. Awesome. And then again, this is going to be the same that we have written here. Then theta t plus again all of these, the centrifugal force square t r d theta omega square. Awesome. Now the other step is pretty much shouting at our faces saying, hey, you know what? In each one of these 4 terms, these d theta is appearing. So meaning that, yeah, that's not going to be 0 or anything like that. So I can just get rid of that thing. And also the second, let's say, simplification I can introduce to these elements is that, well, something that I should consider is getting rid of these parentheses here. So let me go to the next step where I'm going to rewrite the equation, but also I'm going to start decomposing or, let's say, getting rid of these parentheses here. So let's do it. So I have this sigma r RT plus this one here. If I try to, let me keep the same order I was using because I want to reorder them at the end. So equal to what? So, well, I can start multiplying things here, kind of term by term. So the first one is going to be this one here. So this times this times this is going to be RT. So it's the same that we have here. Interesting. Then we have the second one. So we have this times this one here plus sigma r times dr times t plus, now we go with this one. So we're going to have r, this one here, the differential of the stress, this small variation we're going to have there, times t. And then we're going to have, again, the variation of the stress times this small piece of radius that, that is the height of the segment times t. And we are forgetting, or I am forgetting a plus here. And then this is going to be plus this other term here. And so look at this. Another thing that it was also screaming at us, but I didn't pay attention to it, was that, hey, t is also repeated in all of these terms, meaning that I can just cancel these t's appearing here. So again, well, I just wrote them completely, but they're appearing there. And also interesting is that, or what we're going to say is that, hey, in this scale, let's say the scale, in this scale, well, the dimensions of multiplying, for example, these 2 differential terms is going to be very, very small, which means that I can say, you know what, let's consider this multiplication of both of these 2 differential terms equal to 0. They're very, very small. Awesome. And then let me just write it down in a very cleaner way. So we're going to have this plus we're going to have, call it like this. Then we're going to have, let me see, this one here that it repeats plus then sigma r dr. Then we're going to have r sigma r plus again this one here. So I'm missing something here because of the mess that I created. So let's see, this one is this one here. So this one here, I'm forgetting this one here. Yeah, so I have this one here, this one, and this one here. Awesome. Now I could also get rid of this one here that is being repeated. Yep. And that means that if I get rid of those, I can have this here. It's a little bit laborious, but it is worth it to understand what's happening here and what's the effect of all of these variables in the process of determining that stress there. So I have dr appearing in some of these terms. So let me appear here, here, and here. So I'm going to divide both terms by this dr. And that allows me to say, well, this is going to be equal to this. It's going to be equal to this. And this is something that is starting to appear here. And then we're going to have r of what? Well, let's keep it together. I'll keep them together. Sorry about this. This is not theta. This is r. And plus this one here. That's the idea. This one here. Now this is the cleanest we can get it, and I'm going to put the two elements that I'm interested in, that are this one here and this one here. So we are interested in those because we need to know what are the radial stresses and what are the circumferential stresses that are appearing in that configuration. So I'm going to put them together, and let's put it here. So I'm going to say circumferential stress minus the radial stress is going to be equal to what? Well, it's going to be equal to this nice relationship here, r plus this one here. And I'm going to mark it because this is a very important equation. This is the equation that results from applying the equilibrium conditions in the radial direction of the disk. Now, is this equation enough to know what are the circumferential and radial stresses? Well, it's not, because even though we can know the density of the material, we can know the geometry of the material, where we are going to use the radius and all of that, we can know also the angular velocity at which it's rotating, but it is not enough to know what is the circumferential and radial stress at any point of that segment. So, and another thing here is that you see how we're talking about a thin disk, but then at the end, the thickness of the disk disappears, so it doesn't matter the thickness. So this is pretty interesting, actually, to get to know that the thickness of the disk doesn't matter at all in that case. And we're going to see later that, yeah, you know what, even though we talk about thin disks, and that this is not kind of let's say we need to comply with this relation here to call it a thin disk, but the thickness is not appearing here. So why is it important? Can we apply to thick this or not? Well, the situation goes so that we're going to arrive to a couple of equations that depend on boundary conditions, and whether the case is a solid disk, hollow disk, or kind of a specific shape of disk, then we need to always keep in mind that thickness is something we have to have present in our considerations, in our boundary conditions that we need to use to be able to solve the cases there. So, but up to this point, we consider that the thickness was the same across the whole section of the disk. So, well, no, in this case, it disappeared at all. So, but this equation 2, is not enough because we have two unknowns and just one equation. So we need to search for a second equation or another equation that would allow me to match it with this one and then get the values of the circumferential stress and the radial stress. And those equations are the stress strain relations. Like this. As we did with the thick cylinder, we need to see how things they deform in the circumferential direction and in the radial direction. And we're going to call it, well, we have two things. The first one is going to be circumferential strain. And just for the sake of remembering things from our previous lecture, well, you know that circumferential strain, I'm going to call it like this, epsilon theta, and that's going to be equal to what? Well, it's going to be the final circumference, kind of the circumferential, let's say, stretch or something. I don't know what's happening there. Final circumference, I'm just going to abbreviate it like that, minus the initial value of that, kind of the value of the circumference. And then that's going to be divided by the initial one. So we can get the strains according to the original definition of what a strain is. So divided by the initial circumference. And then in the case of the radial stress, or sorry, radial strain, well, I'm going to call it epsilon r. And that's going to be, well, it's going to be the width, the height of that segment. So it's going to be the final, let's call it radial width, like this, minus the initial one, radial width, divided by the initial one. Because now we can just follow these definitions into getting a formula for them. Awesome. well, so let's define them both. So let's start with the circumferential strain. So I believe I could make here a small piece of segment like this. Okay, so this is the original undeformed one. Awesome. But then when that starts moving and all these stresses appear and the whole, let's say, rotation is applied to the disk, then this is going to deform it's going to deform in something like this. How to put it? I could say that it's going to deform something like this here, maybe. Let me see if I can draw it nicely. So it's going to try to expand. So it's going to do something like this. Going to exaggerate the deformation of this. Because of the rotation, all of the stresses appearing there. So this is very exaggerated how this is going to expand. Yeah. And then we knew that, well, this is the radius that we had here. Yeah. So then we're going to have a few important measures here. So we're going to have that this one is this is some sort of a deformation in the radial direction here. So instead of starting at r, it's going to start at r plus u. But then in this part also, when it finishes in dr, so we're going to have also a du here. Yeah. Awesome. Then I'm going to tell you later what's going to happen with with this part here. Yeah. Because it's going to be affected differently, even though I draw it like that, but it's going to be a little bit different. So let me move this one here from here to here. Okay, so who is the final circumference? So let's start with the initial one, actually. So we can see it right away when we ask the question about who is the final one. Let me put it like in here. Well, the initial circumference is, well, this measure here. And that's going to be what? Well, it's going to be equal to 2 times pi the radius. So basically, that's the initial circumference. So 2 times pi the radius. So meaning that if this is the initial one, this is going to come here. But then what is going to be the final one? Well, the final one is going to be the multiplication of, well, 2 times pi, well, we're talking about the full circumference of, the resulting part of, or how it moved or how it grew this segment here. So this is going to be equal to then r plus u. Then if we do certain simplifications here, like this one, this, and then I could just look at the part. So we're going to have r plus u minus r, and this is going to be divided by r. So at the end, this is going to be u divided by r. Let me write it down completely here. U equals to divided by r. Let's put a mark on them. And then in the case of the radial, say, deformation or strain, so let's start again with the initial radial width, yeah, because so we can see the final very easily. So I'm going to have here this. Well, the initial radial width was all of this, and all of this is dr. So it's going to be dr here, because that's the initial one. Well, what's the final? Well, it's going to be dr plus this small variation here. So dr plus the small variation there, that is du, like this. And again, I could work it out and say, well, this equals to dr plus du minus dr, and this is going to be divided by this dr. But at the end, so I can do the same like here. So this divided by this subtracted with this one, cancelled out, and this equals to this one here. Then let me write it down again, this one here, du divided by dr. And I'm going to mark it also like this one. And let's call this, so we were already in equation 2, let's call this equation 3 and equation 4. What questions do you have? None. Okay. Now, this is one definition, geometrical definition of the strain. But also we can have a definition of strain based on stresses. So how much the stress and the material will cause a strain. And again, I like to write down this part because remember that we have forces that create stresses, sorry. Then we have a material here. And then stresses on the material create strain. And this creates deformation. It means that we can look at a phenomena from 2 points of view. For example, if we're talking about strain in this case, we can look at it from the geometrical definition of the strain, which is what we have already done, or we can look at it from the material stress definition of it, something like this. And then we already covered this. So to this belongs equations 3 and 4. But now, yeah, well, this doesn't tell me anything because for me it would be very complicated to know what are those values of u. So definitely I can know what's the value of r, but what's the value of u? What's the value of delta u or delta r? So I don't know those. So I need to find another way to look at things so it could provide me more information about the problem. So let's look at from this point of view of the stress material relationship. So by definition, this, let's use another color, this one here. The circumferential stress could be said to be equal to, when I use a typical Hooke's law relationship between stress and strain, considering again the material is steel and is isotropic. So I could say, well, it's going to be equal to the difference of these stresses minus the Poisson ratio here and R. And then we get the first definition here. And then the second definition would be that this equals very similar to it that we have seen in the past, like this, and then this one here. Then let's call them question 5 and equation 6, because let's surround them to match our starting point. So let's put it like this, and let's put it like this. So definitely, if these two things are the same, then what is next to do is say, well, now I can say that 1e, or 1 divided by the Young modulus, times these stresses here, well, this equals to what? Well, to u divided by r. This is where I mentioned that now these are equations 5 and 6 here. So we're looking at one characteristics of the whole definition from 2 different point of views. And then if I continue handling those, or not, let's just write the other one here. So this equals to this minus Poisson ratio times the theta equal to what? Well, to this quotient here. Awesome. So let's work them out. So let's work this set of equations out, because this might be, I'm having again the sigma theta stress, circumferential stress, radial stress that I need to solve this equation number 2, which is the equation coming from the equilibrium of forces inward and outward in the radial direction. And then, but still now I'm having this u and r, well, and delta u as some certain unknowns that I need to try to see what's going to happen with them. Yeah. So let's see. So where should we start? Let's start with this, the first one. Yeah, it looks better. Yeah. So I could say that, actually, I should give it a name also here. 6, 7. Let's work with equation 7 or 6. Here it is. So we have that. Then I could isolate the u and then put the r to the other side, so I can write it like this: u equal to r divided by e, Young modulus of this part of the term here. Perfect. Then let's look at this. Well, let's clean it a little bit because we need to get rid of certain things here, and you're going to see why. So let's put the e in the other side, and that's going to end up doing like eu equal to r times this, or the terms in these parentheses here. And you're going to see what. Now, if I differentiate these, let me differentiate it with respect to r. So what's going to happen is that both sides of the equation, I'm going to have that e du dr is going to be equal to what? Well, this something's nice happening here, because when I differentiate this with respect to r, I need to differentiate this times this, kind of apply the chain rule here of differentiation, and that's going to be end up here. Well, let's differentiate the first one. So differentiate derivative of the first one multiplied with the other or the second term without derivating it, and that's going to be equal to this. The derivative of r is 1, so it's going to be this one here. Then this is going to be plus the first term, no, without being touched by the derivative, multiplied by the derivative of this one here, this term here, and I can apply it directly here, so it's going to be this term here. So just the application of the chain rule minus then this one here and derivative of this one here and this one here. All right, but okay, this is interesting. Now, if you take a close look at this, by the way, is there any questions? Are there any questions? If you take a look at this term and look at the equation 7, look at this interesting thing. So I can just get the same term working with equation 7, meaning that I could say that E times du dr, this comes from equation 7, equals to what? Well, it just equals to these two terms here. So now we have got written of du by doing this. Imagine that. So if I introduce this one back here, so I can say that sigma r minus this Poisson ratio times the circumferential stress, so this one here, equals to what? Well, it's going to be equal to all these things here, so I can write them down again completely. And things I'm getting much more clearer in that sense. So this one here and this one here, dr. Great. Now let's put everything in one side of the equation and see what can we get from everything. So this is going to be one of the longest runs we're going to have, but we are going to get to, well, we finally going to get to the equations we need to get in here. So let's do it. So just hold on. So let's do it. So let's move back. Let's move everything to the one side of the equation here. So if I try to minimize time that we have to spend here, I will try to. So I can copy this and repeat it here, and then I can delete this equal. Where's this one? And then definitely what this is going to end up being is that, well, I have this thing here, I have minus this thing here. Is it? If I move it to this side here, yeah. And then you see, yeah. And then this stays the same, and then this is equal to. Because this is not the way I want to have it. So let me do something here. So actually, let me move just this one to this side of the equation. And to that end, if I move it to that side of the equation, this is going to be end up being, let me just delete this part, because this is not the way I want it to be, because I would have to do an extra step that I don't want to do. So, okay. So I'm going to keep these ones as they are, but I'm going to move this term to the other side of the equation. So let me write it down. So I'm going to have this one here, this one here. I'm going to write this down, so this is going to be minus, yeah, this one here, plus this one here, then plus this one here, yeah. Now this is getting to the shape I needed. This one here, minus this one here. And this one here. So the reason for this change is the way we have defined, or why I didn't want to proceed in the other direction, because I needed to do an extra step. It's because the shape, look at how we have defined our difference of stresses here in equation 2, and then I want to keep kind of the same order there, at least at a certain point. So let's then try to find common terms, and this is equal to 0. There it is. Then let's try to find common terms there. And one thing that I can realize is that, well, you know, I'm having circumferential stress here as common terms, like this one here and this one here. So I can write them like, okay, this is going to be equal to the circumferential stress times 1 plus this one here. Awesome. And then I have as other terms or common terms, these two here. So I can write them. So if I take out the minus sign, I can write this like this, and then in the end, it's going to end up being something like this. Yeah. Now it's getting much more, let's say, clean and clear there. And then again, let me write down everything as we have it here. So we write this one here, plus this one here, and then Poisson ratio equal to 0. Now I can take a another common term, which is this one here, you see? And I can write down like, oh, you know what, this is going to be equal to, look at this, that's why I wanted to do it in the first, say in the change, look at, it's the same term that is appearing here. This is something that I want to have there. So this one plus this one here. Yeah, and then again, well, I'm going to keep writing this one by the r minus this one here, dr, equal to 0. Awesome. Very good. But now, why would I want that? Well, these are the equations that come from, actually, let's give it a number here, because this is a very important equation for us, because this is the other equation that we were looking for when we started working with the stress-strain relations. So, and we are already in equation 7, so this is equation 8. Yeah. So we needed a second equation to get to know how much was the, let's say, where the circumferential and radial stress. Because with this whole equation, we couldn't do anything, but now we have a second equation. So which means that if we have two equations and two unknowns, it means that I can solve the system of equation and find values for sigma r and sigma theta. Awesome, let's do that. How do we do it? Well, working with equations 2 and 8. This one are the same thing. Well, not the thing, but this is the other relation I wanted to have. I have this term, so meaning that this term here, if I copy this, so this term, like this. So I have equation 2 here. I brought it back, or brought it down. Meaning that, hey, this term here can be extracted from equation 2. Then I could write that what? Well, if this equals to this, that's why the whole intention of everything here, then it means that I can substitute all this part in here, and it would get me, let's say, a much more, let's say, clear picture in here. So let's do it. So I'm going to have, let me use a big, well, yeah, it's going to be, so the difference between the circumferential and radial stress equals to this, so I can write this down like this, plus this term that was coming from the circumferential centrifugal force, plus what? Well, plus this one, theta divided by differential of radius, Poisson modulus, and this other term here. Right. What should we do? Well, let's start splitting things apart so we can get rid of all the parentheses we have there to see what cancels out with what can be grouped together again in a more convenient way, and so on. So let's do it. So let's then multiply these terms here with each one of these, and then let's multiply this r here with each one of those. So let's see. So at the beginning we have this one, r here, sigma r divided by the r times this one here, plus these other terms. So nothing special being happening here, just a bunch of rearrangements, plus this one here, the r minus r Poisson ratio, and then this term here. And this equals to 0. All right, so what's happening here? So let's keep separating things, because there are some equations there that we might be able to get rid of things. So now let's split, for example, this part here. So just this part, because there are some common terms that we might get rid of them. So let's do it. So we're going to have them then that r, so the r, this times 1 is the same, plus r, this one, times this other Poisson ratio. So we are going to have this one here. Great, and then plus the rest of the things. just rewriting everything minus this one. Now look at what interesting is happening here. So we are equal to 0. We have this element here, and we have this element here, which are the same. So we can cancel them out, this one and this one. So we are getting to a more reduced version of things. So let's do it. So r, the r plus this term here, plus this term here, and this equals to 0. Now what we're going to do here is we are going to kind of clean up a little bit more these, let's say, these other terms. So I'm seeing here that we have, for example, the radius here, I have the radius here, and the radius here. So let's divide by the radius, by r, by r. So if we do that, we're going to end up with this nice equation here. Plus density r omega square, this term here, plus then this term here. No, nope. This one here, equal to 0. And if I write it a little bit better, so to see things, I'm going to move this one to this part here, because now it is going to be evident what's the next step is going to be here. This one here plus this one. So now I have these stresses, or the definition of these stresses, where I wanted to have them, and all of these two stresses are kind of, again, well, there are still a couple of, let's say, unknowns, but there's something interesting here. I could try to remove this stuff by integrating with respect to r. And if I do that, then definitely this is going to be, this is going to end up being, or done, or doing, is that, well, I have r here. If I integrate this with respect to r, so this becomes this one here plus this one here, yeah. And if I integrate, but I also send to the other side, this is going to be equal to minus this density omega square. Let's put this one here, and also this r. If I integrate that with respect to r, this is going to end up being this one here, plus an integration constant. I'm going to call that C1. Say, well, but you know what? You're still having two unknowns, and now we have three unknowns because now we have an integration constant, and we yet don't know how much is the value. So we were in equation 8. We don't know yet the value of this, so this is equation 9. But what about if I bring again the equilibrium equation, equation number 2? We copy it and put it in here, like this. Let me put it a bit apart. Yeah. What about now having these two equations? If I subtract equation 9 from equation 2, so what is going to happen? So let's do it. Where right? We should write in here. Yeah. Subtracting equation 9 from equation 2. So let's see, well, let's first subtract these to the left side. So this one and this one. So what's going to be? So it's going to be here, sigma r plus sigma circumferential stress. Yeah. Then the minus this one here, which is circumferential stress, plus radial stress. And that's going to be equal to what? Well, to all of this minus all of this. As simple as that. Yeah. So that's going to be what? Let me see. This is going to be square, this one here, r square divided by 2, plus the integration constant from the previous step, yeah, minus this term here, r, sigma r divided by differential of radius, then minus then this term here, and the term here is this one here. So let's see what common things we have in both sides of the equation. So the first thing to notice is that these two things are canceling out. So now we are not working with two unknowns, but now we are working with just one unknown. So now what we have to do is to rearrange things and get rid of things as much as possible, so we can, let's say, stay with a very clean equation that we could use to solve or to find out what's the value of that radial stress. So let's do it. So when I do this, I end up having two times the radial stress, and that's going to be equal to, in here, let me see. So I have this one here, I have this one here. So let's see, common terms. I have as common terms, I have this one here. Yeah. And then I have, how to put it, this one here. Perfect. So what I can do is work it out in a way that I could bring also this part here. So this is going to be equal to what? Well, to be what? Let's call it is minus this one here. Minus what? Well, it's going to be minus the common term, which is this one here. The density times the angular velocity there times the radius. Yeah, and then I'm going to bring these two here at once because I want to leave it as clean as possible. And then that's going to come up like plus v. So if I multiply this times this, it gives me this term here. But if I multiply kind of this is not giving me this term here. So what I need to do is add a 2 here, because now it's going to give me all the terms I need to have, plus C1 minus this term here. Awesome. Pretty awesome. Now, let's put the terms that are of interest for us. In this case, is the terms related to the radial stress in one side of the equation, and then put it in then leave the rest in the other side of the equation. Let's do that. So let's put this one here. So let's say 2 r plus r, this one here. And that's going to be equal to the rest of things. And now I can sum these two terms here. So minus 2, and this is going to be 3 plus the Poisson ratio plus C1. Now I'm seeing also certain similar terms here that I could reduce at some point, and just bear with me, because one of the things we can do here is that if we multiply by r here, so what this is going to do is this is going to give me 2r, because these are some similarities with other equation, r squared, this one here, equal to what? Equal to this density, angular velocity, now this term, by 2, 3 plus Poisson in here, plus now r. The reason for that is because it is obvious that we need to integrate again to get certain definite values here. So one of the reasons to do it would be to, I want to keep this constant 1, because that's going to give us a nice set of information at some point. So let's do this. So then in this part of the equation, this is actually, well, it takes a time to see it, but this is actually the result of applying the chain rule to a multiplication of two terms. And those two terms, if I, how to put it? If I, let me write here, if I integrate this, again, with respect to r, of course. So this is kind of, this can be represented as something like this. This is the result of the application of the chain rule of a product. And this comes from here. That's why the multiplication by r and everything by that. So this step is going to be performed downstairs. So, but this is the, let's say, when you perform this derivative here, you're going to get this. Yeah. So we haven't performed the integration yet. So 3 divided by 2, 3 plus Poisson ratio plus this one here. Now, if I integrate this, now I can integrate this, then, so let me just make a note that this is done just to get this part here, yeah? Just to get this part here. Then if I integrate this, what's going to happen? Well, the integration of this is going to end up being this one here. Now, if I integrate this with respect to r, so definitely, well, this is changing with respect to r, so this r to the power of 3 is going to turn out being power of 4, yeah, divided by 4, and then this one divided by 2, just to separate those terms, then multiply this one here, plus the integral of this, well, this is going to be r squared divided by 2, like this, there's integration of that, plus another integration constant. Now, if I take this r squared and bring it down to each one of these terms here, so let me just, so dividing by r squared. So this, look at this. Now we have one, how to call it? Well, let me write it in 2 steps first. So let's first do this. Now we have one equation, one unknown, that actually the whole purpose of all of this was to get to this point. So we get to know how much is the radial stress. Of course, there are a couple of integration constants here that we need to, let me see, plus C1 divided by 2 plus then C2 divided by r squared. So there are a couple of integration constants that we need to solve for, but we have one equation and one unknown. And when we talk about integration constants, definitely we can find the values of C1 and C2. Then what this is said is that, well, now we got an equation for the radial stress in terms of C1 and C2. And then we were at equation 9. Now we can call this equation 10. What questions do you have? Okay, now about how we find now the formula or equation for the circumferential stress. Well, again, equation number 2, our best friend, this one here, I believe I still have it in, yeah, in the clipboard. So this one here. So if this is the value for the radial stress, then I could input that here in this equation, and that would give me at least one value for, possibly, for the circumferential stress. So let's do that. So let's bring joint or working, let me write it down here, with equations 2 and 10. Okay. So it means that I can say that the circumferential stress, if I then take this radial stress to the other side here, I can call this, well, this is going to be equal to so this is negative, it comes minus this, so minus this. If it's minus this is positive, negative, negative, means that, okay, so it comes to this side like, let's see, yeah, minus, where is it? Yeah, or let me write it completely as, yeah, it could be, well, maybe completely like this. I'm just trying to figure out what's the most clear way here. Yeah, let's write down this one here in this form. 1 divided by 2 plus this one here, r squared, minus this one here, right? This divided by 8. Yeah. Perfect. Now, I could say that, let me look back. Yeah. I'm trying to, oh, wait a second. This equation 2, it will make the trick here. Sorry about this. It's not this one that I need to figure out because it would give me a quality, but it's equation 9 that the one that I need to bring here. This one here, to paste it here. This, let me clean it a little bit. So this one, yes. Yes, perfect. Now I can say that working with equations 9 and 10, like here, yeah. Awesome. So now I'm writing down all of these equations. Well, I have written it down here. Then this is plus this one here and equals to this side of equation. So like here, square, just rearranging these terms here, 2, and then this is 1 plus the, then this one here. Yeah. Then let's just solve for the circumferential stress in this one. Okay, now we can write everything. It's a bit long, the procedure, but it's not complex. And at the end, we're going to get to see where all of these elements are going to minus, plus, yeah, going to appear here. And then, so we are putting everything this side and then minus, yeah, this part here. Actually, solving these exercises are way more fun than what we are doing right now. Yeah, this one here, plus C1, yeah. Excellent, excellent. So now what? Well, let's join common terms and let's try to just solve for the circumferential stress. And we're going to get to that equation that defines how much is the circumferential stress in terms of the radius. And then we need to jump into one interesting concept. So let's keep working with this one. So one thing we could do here is take common factors here first. These terms here, for example, subtracting C1 divided by 2 minus C1, or vice versa, so sorry about that. So this is going to be equal to the very same C1 divided by 2. We cannot do much with this one here at this point. And then we're going to have this other term here. So I have common terms here. That's something like this. So it means that I can subtract this larger term divided by 8. And that's going to multiply what? Well, it's going to multiply this thing here, 3 plus b, sorry, this one here. Let me use a, not that bad. This one here. Then times this, but I'm using an 8, so I'm missing a 4 here, so which means that this needs to be minus 4 that multiplies this one here to make it legal. And plus, well, plus nothing because I already worked with that one. Yeah. Now let's get rid of these parentheses here. Again, this stays the same. Stays the same. Then we work with this one. And let's see. I can say that this equals to what? 3 plus the Poisson ratio minus 4 the Poisson ratio here. And then it means that the circumferential stress is going to be equal to, again, to this term that doesn't change. This term here minus this term here. Now then we have here what? Well, we have, sorry, this is a plus here. We have 3 minus 4, that's going to give me minus 1. And then this minus this one is going to give me, again, minus 3 times the Poisson ratio. And finally, we could write that our circumferential stress equals to this one here. And that would be partially it, because we don't know yet how much are those integration constants C1 and C2. So this minus this, and then I'm just going to take this minus out of these parentheses here, and then it's going to be minus r squared divided by 8, and this is going to be 1 plus 3 Poisson ratio. And now we have found our equation for the circumferential stress, and this is our equation 11. We have, let's bring them together here, this one here. Now, if somebody asks us, how much are the circumferential and radial stress, then we need to, well, we have the two equations. The only thing needed to be done is to find out the values of the integration constants. And it means that we need to work with boundary conditions. Let me write a couple of boundary conditions then that's something that you're going to do during the exercises, but it is important to write them down here. So possible, let's call it possible, or no, boundary conditions. For just two cases, for example. So for example, in the case of a solid disk is a disk that has no radius 1 or internal radius. So basically, is that what it means? So the first kind of boundary condition that exists is that as the radius, for example, imagine that we are evaluating this radial stress or the circumferential stress in radial in R at the center of the solid disk, meaning that the radius is 0. So that would create an indetermination of this segment or this part here, this term that is the constant 2 divided by square radius, because if you have 0, then it creates an indetermination, means that the first boundary condition that you're going to have, or the boundary condition by consideration, is that this C2 is going to be equal to 0, because you cannot have it any other way. Yeah. And the other, let's say, boundary condition is that when radius equal to R2, meaning that when we are talking about the periphery of the disk, if I draw a disk here, and I said, well, you know what? This is the radius 2, then it means, and actually this would be nice to have it here. Solid disk, yeah. Then in radius 2, or at this point, the radial stress equals 0. And why the radial stress at that point is 0? Well, if you remember from our lectures in thick shells, if there is no any pressure or forces applied to the outer surface of the disk, then the radial stress is 0. And that has to happen. So then I have my two boundary conditions, or meaning that if I know that at R2, the radial stress is 0, meaning that if I substitute R2 here and 0 here, then I get how much is C1. So I can solve for that. So that's one case. In the other case, we have the disk with a central hole, a central hole. So this means that if I draw that disk here, like this, and I draw another one to represent the internal hole, yeah, then I'm going to have R2, and I'm going to have R1. Yeah. So in the same case, under the same logic that was said that the radial stress at the outer surface of this disk is 0 because there is nothing applied there, then in this case, when R equals 1, or let's try it correctly. So when R equals to R1 or equals to R2, then the radial stress is 0. And then I can use these two boundary conditions in these two equations to get the values of the circumferential stress and circumferential strain. There's a nice derivation for each one of these cases, but it's longer than what we have done so far, so we won't have time to do it at this point. But this is the way to deal with these type of problems. What questions do you have? No. Now, let's take what is the rest of the time to discuss about, okay, if you take a look at what's happening with the stresses, for example, in any of these cases here, let me try to draw how the stresses are represented, for example, when there is a solid hole and when there is a disk with a central hole. So we get to know how the stresses are going to be substituted there. So for example, for the case of a solid disk, let's call it solid disk, then what's going to happen is something like this. How to put it? So we're going to have the Let me bring a Cartesian coordinate system. Like this. And if we call this that this is the, I'm going to put stresses here, and I'm going to put the radius here, considering that this is something that, well, because all these stresses are going to vary with respect to the radius, then the radial stress is going to do something like this. It's going to come from here, and it's going to do something like this. And this is, the radius starts from here to the top. The radius is measured like this. So, and this coincides with the axis of rotation. Awesome. Now the circumferential stress is going to do something like this. So it's going to start a little bit like being here. Of course, this is not at scale, but this is going to do something like this. So let me mark them down. So this is sigma r, and this is sigma c, or circumferential theta, sorry. And this is for a solid disk. And let me write down that this is, well, the r is measured from here. There you go, yeah, awesome. Meaning that when you get a figure or you plot those values, in that sense, you need to find that they're going to follow some sort of this shape. Now, what happens with the disk with the central hole? Yeah, so let's see how much is that those values there. So it means that we need to bring again a Cartesian coordinate system to be able to draw this. There are certain values that we need to, or we could. There it is. Then again, this is stress. This is the radius. Put a little bit up. So let's move it. Right here. Yeah. This is disk with central hole. Yeah. So in the radial axis, we're going to have a couple of points. For example, we can have here and this one here. So this one corresponds to R1 and the other one corresponds to R2. So this is going to do something like this. So this is going to be R1, and we're going to have also R2. There you go. So when this is the maximum stress, no matter what, which one of those, in this case, this also is going to have a maximum. It's going to do something like, let me try to, where this is a maximum, and this is the maximum, sigma radials maximum. That it is not located at the average of both of them, not necessarily located at there, meaning that this is not necessarily the average of both of those two elements there. Yeah. And then the circumferential stress is going to do something like this. Circumferential stress, and then this is the radial stress. And in this case, in this with the, well, actually in both cases, we could say that we keep the same order by magnitude as in the case of thick shells, where the circumferential stress was always larger than the radial stress. Awesome. Now, we need to come back and see one specific application that, okay, if I know that the radius, or these stresses varied along the radius, and then some of them, like in the application with a central hole, which is pretty similar to the video we saw at the beginning of the lecture, where the disk exploded or disintegrated by the high velocity, angular velocity, then you see that the circumferential stresses are way larger, meaning that we could use certain failure theory to determine if that's going to fail or not. But one interesting question that people formulated is, can I have, or can we have a disk with uniform, let's say, stress distributed along the radius? Meaning, what about if I could have a disk, and actually they call them disk of uniform strength. Talking about strength, when strength are kind of the, how stresses relate to the material properties. But what about if I can have a shape of the cylindrical, let's say, area when seen from the side, that no matter where in the radius I point out, I'm going to have always the same stress. So meaning I'm not going to have this big difference between the circumferential and radial stresses. So such disk you can find in the literature on many forms, but one that you can find is something like this. So what about if you have a disk that is like something like this, and then it just comes like this, just exaggerating this figure like this. It has our central part here, and then this repeats 2, 1, 2, 3, 1, 2, 3, something like this. Of course, it's symmetrical because it's a revolution, so something like this. And then we have, for example, the axis of symmetry in here. This one here. And let's draw another axis of symmetry, definitely, because this is symmetric. Like this. Where this part here is about T. Here. Well, let's not call it T. Let's call this that to make this better. Let's give some properties first. So let's imagine that this has certain radius here, something like this. These are radius 1 here. Let's imagine we write it better. And then we pick a segment here between, because we want to know how that changes. And then we call this, well, you know what, this part here is, let's call it T. And let's call this part T plus a differential of T. Even though, this is a term, could be positive or negative, so it depends on how you define the terms here. There's a T. And then, well, from this point to this point, this is going to be the radius that I'm interested on. And this part here, let me draw it from here. And then this other part here, the thickness of this element, this is going to be the radius plus the increment of the radius there. And let's call this part also, to give it a name, because this is going to be very important, that this is going to be the hub or something here at the center. This is going to be T0. Again, just to mark it, this is the axis of rotation. Perfect. Now, again, if I'm talking about that part, this is looking at the disk from the side, because this would be something like looking at it from the side. So this would be a disk of something like this, where I would have the center, something like this, yeah. And I could keep kind of moving this symmetry line. There, and also the vertical symmetry line, or line of symmetry. Here, awesome. Something like that. So just, well, let me see if I could move it just a little bit to make it more congruent. Yeah, something like this. All right. Then let's imagine also that we are taking this small segment here, and I promise this is going to be shorter. Yeah, that is defined here. And let's see what the equilibrium says now, with the consideration that stresses are going to be the same no matter where we are going to be working with. So I'm going to bring down this one here, because we're going to need it. It's pretty much going to be more or less the same, with certain differences. This one here. Now, one of the things that is going to happen when we make the consideration of a disk of uniform strength, as it's called, or basically what it means that no matter where you step on the radius or in the radial direction, the stresses are going to be the same, is that, where should I write it here? Yeah. Is that the radial stress is going to be equal to the circumferential stress, and we can call whatever it is sigma. So because no matter where you step on the radial direction, you're always going to get the same stress value, meaning that you could use a disk of uniform strength, they call it so. So you are not going to get such figures like this one for values of radial or and circumferential stresses. Yeah. So it means that then this doesn't exist. This doesn't exist. So there is, because I'm going to call it that they have the same value here. This doesn't exist here. Yeah. The rest of the terms stay. So what happens now if I do the equilibrium analysis for this case? Well, in the phase here, in the phase defined by the segment AB, what's going to be the force there? Well, the force is going to be the stress times the area of this phase on the bottom, and the area of that phase is going to be R delta theta T. That's it. Yeah. In the upper part, defined by ZD, and then the phase CD, then we're going to have that is equal to, well, the same that we had before, but now we're not using any differentiation between radial or circumferential stresses. T plus dt times this one here. And then in phases BD and AD, which in the lateral phases, we're going to have that is equal to this. Now, if we work with the equilibrium again, of the inward equals to the outward forces, and remembering that the centrifugal force is this one here. Yeah, so this segment here. Let me put it here. Call it centrifugal force. Then let's write the equilibrium. So, oh, I'm sorry, my notebook, OneNote crashed, but it's starting again. So let's give it a few seconds. Sorry about that. There it is. Didn't like the copy and paste. 75. There it is. Sorry about that. Centrifugal force. Then inwards equals to outward forces, and we're going to get that inward forces are going to be AB and BD AD. So those are this one here, T plus 2 times, again, the same deal with these two forces here. So they're going to be sigma T dr sine of differential of the angle here. And it's going to be equal to what? Well, to the outer force CD here. Let me write it down, this one here. Plus the centrifugal force. R squared T dr, no, okay, yeah, the R, the theta, and omega squared. Just writing it as it is presented here. Awesome. Again, we know that the same distinctions we did previously, that the sine of this angle can be considered also the angle itself, because it's very small, that angle, and we can do that kind of substitution there. And let's keep writing. I promise it's going to be way shorter. So it's going to be this one here. This 2 is going to cancel out with this one here. And then the sign is going to be substituted. So this is going to end up being this one here. Sigma T dr, this one here. Yes. And then, where else do we have? Equal to, should I do this at once or what? Let's do this at once. So let me take this out once and for all, or not, because I want to do something first. So let's just here, let's get rid of this. Oh no, well, it's not correct, because I haven't made the substitution, so well, I just wanted to save some time, but let's do it like this. Time plus dt square omega square t dr. Now I see that the angle it repeats in all of the terms, so I can just get rid of this, this, and this. Yeah. So let's continue. So I'm going to have this one here, to have this one here. Sorry about this, and I don't want to make this mistake that, yeah, the r equal to, and let's get these together. So this is going to be this times this times this, or let's put this together to have some order, plus r dt plus t dr plus dr dt plus this term here. Again, this term is too small, so we are going to just not take it into account. And also, let's see what terms. Let me finalize the multiplication of the stress with this parenthesis here. Then sigma r dt plus sigma t dr plus this term here. Awesome. Now I know that these terms, for example, this term here is repeated here, so I could cancel them out. Yeah. Then this one, and also that this term here is repeated in, where is it? In here, so I can cancel them out. This one here. Sorry, not there. This one here. So it means that if I just take these two parts, this is not a minus. Just a second, that my, it is kind of failing. Okay. If I take these two elements here, this one here, and this one here, are remaining, I could say that minus sigma r d3 equals to this component that comes from the angular centrifugal force. The machine is not working like this one. Yeah. Now what I can do is that I could take, because I'm interested in the thickness, so how much should the thickness variate along the radial direction, so I always get the same stresses as the premise we started with. Then I could say here, well, I'm interested in the variation of the thickness. So in this case, the thickness is not disappearing as in the previous case that we disappeared the thickness. So I have the t here, I'm putting the t down here. So this is going to be equal to minus what to density, angular velocity, radius, yeah. Then this dr, and this is going to be divided by sigma times r. So I can cancel out one of these r's with this one, meaning that then the derivative of this, I'm interested in the t here, equals to this one here. And this is divided by the stress. Awesome. Now, if we integrate both sides, so the left side by t and then the right side by r, so this is going to, well, we have the inverse of t here, so that's going to require the bringing logarithms here, so integrating both sides. So what we'll have, that is, then that the natural logarithm of t is going to be equal to, I'm going to separate them so to make them as they should. So this is sigma times r squared divided by 2 plus c. Now I can make, as a constant, I can make c the natural logarithm of c, and then I can put it to the other side, meaning that I could write this like this. R squared divided by 2 sigma. Applying logarithm properties here, I can write down this like this. Which means that I could then, elevate or use the natural exponent here to get rid of the natural logarithm here. And this is going to end up being this one here. Or this one here. The velocity radius divided by 2 sigma. And this is our equation. Which one was it? There. Let me check. Equation 11, equation 12. So this equation is going to tell us how much should be the how much should be the radius, but sorry, the thickness is 12. So we are always going to get a constant stress along the radial direction. If we want to solve this, for example, for a case, or for the case that we are depicting here, this one here, and I say, well, I have an integration constant, so I need to use some boundary conditions. So let me write down here. There you go. So one of the things we need to know is that when R1 equals to, or when R equals to R1, meaning at the beginning, the thickness is going to be a known thickness at T0 that I know, because constructively, I know how much is this T0 because that's my design. So I say, well, it's going to be 20 millimeters, it's going to be 25 millimeters. But then after that, growing radially, that thickness is going to be changed, or it's going to change. So stresses are always the same along the radial direction. Yeah. So those are boundary conditions, things that I know. So if I substitute this into this equation, equation 12, what I'm going to have is that, well, that T0 equals to 0 to C. Just give me a few seconds that my computer is dying, and it might be possible that it doesn't want to write anymore. So it's going to be C times E minus density ds, and then R1, because we're evaluating this at R1 divided by 2. Sorry, divided by, oh my goodness, this is failing badly. I don't see even the cursor. There you go. Yes. Meaning that the constant that we want to get to know there is going to be equal to what? Well, it's going to be equal to, just going to move this term to the other side. So it's going to be T0 times E square 1 square divided by 2 sigma. Awesome. Now that I have the value of C for this case, I can reintroduce it back to this part here, to equation 12, and that's going to give me finally the formula to describe the thickness across the radial direction. So reintroducing in 12, so that's going to be that T equals to C, but C is this one here, so it's going to be T0 E this one here divided by 2 sigma. Let me try to delete this one here. Yeah. And that's going to multiply what? This one here. R square. Remember that this is 1 here. Sorry. Yeah. Divided by 2 sigma. Awesome. Now I have these nice 2 terms that basically I can group them, and they are finally going to be presented as the T, or the thickness of the disk for this specific case, because remember that every time we discuss about this, we have to discuss about boundary conditions, and that's why these equations are general, so it allows you to adjust them to the case you have at hand. So this is going to be equal to the initial thickness, or the thickness of the central part of the hub that you are defining, times E. Again, this, I could just, to put it in order, this could be plus or minus, but the difference is in what you put in the parentheses, plus or minus in the end. So this is going to be 2 sigma times R square minus R1 square. And this is one important equation for us. If you plot this equation, given those known values, then you're going to get a nice curve that's going to tell you how the thickness is going to vary across the radial length. Well, it took us close to the 2-3 hours, but there are still many things to do here that I prefer that you do it during the exercise lessons, because in there you have to apply boundary conditions for certain cases. You have to find out what is the maximum angular velocity you could drive something, or you're going to find what's the thickness you need to have so it doesn't fail. So those are nice examples to have. And also remember that why this is important. You might not be working never in the future with these grinders or rotating discs, but it's important to know that if you see such things and you're working with such things like you yourself operating them, so the safety features and the potential, let's say, accidents that may happen with them. And we have defined here the formulas that will allow us to know stresses develop their maximum angular velocities and thickness. So imagine that. So it's been long, but we managed to do it. So what questions do you have? If not, I wish you a nice weekend. And next week, I believe we have classes on Thursday because Friday is Easter. And so we have classes on Thursday instead of Friday. So take care and see you next Thursday. Bye.